Delighted to introduce our work, Fast Startup of Passthrough Network Virtualization for Secure Containers. Nowadays, cloud providers are using containers to host user applications. These containers necessitate cloud network to interact with other cloud services like the cloud storage and complete the tasks requested by the users. The cloud network is vital to the performance of these applications. The containerized applications have two major characteristics, including a short lifespan and bursty invocation requests. According to the statistics from Alibaba Cloud, over 3/4 of the applications have execution time less than 10 seconds, and over 200 invocation requests can arrive on a physical machine simultaneously. And this leads to the requirement for the network not only to achieve the high data plan performance, which is a basic requirement, but also high deployment density and also fast startup. Container network based on single root IO virtualization or SROV technology can satisfy the three requirements for the traditional containers. The SROV technology can virtualize the resources of a network interface card into multiple virtual functions. And compared with software virtualization, SROV provides stronger performance isolation and incurs lower data plan overhead. And with supporting technologies like scalable IOV, the number of virtual functions that can be created on one network interface card has increased from about 200 to over 1,000, providing a high deployment density. And finally, the setup of a virtual function for a traditional container can be fast, because the virtual functions are processed by the host network driver to pre-create a series of Linux network interfaces. And the major setup procedure for a traditional container is simply moving those interfaces to the container namespace. But however, when we enable SRV for secure containers, it can cause severe startup problem. Secure containers, unlike the traditional containers that use the C-group technology to isolate the resources, the secure containers like the Firecracker and the Kata containers, they run their process inside a micro virtual machine, and they use independent kernels to provide stronger isolation. According to our measurement, when we enable SRV for the secure containers, they can significantly increase the startup time, particularly under a high concurrency. For example, it can increase the time of starting 200 containers by over 3 times. And this motivates to ask what causes the overhead and how do we accelerate the startup. To do that, we need to first understand what is special with SRV-enabled secure containers. As we have mentioned, the traditional containers, they share the host network driver, and they manage the virtual functions through the shared host network driver. But the secure containers, they have their own kernels and their own network drivers. So they want to manage the virtual functions using their own driver. And for higher performance, they want to bypass the host network driver and directly interact with the virtual functions, like directly passing control information or directly moving the data between the network interface card and the guest memory using the direct DMA technology. And this process is called Passthrough I/O. According to our measurement, we find that it is a configuration of Passthrough I/O that causes the high startup overhead. We break down the startup of 200 containers, and as shown in this figure, the x-axis is a timeline, and the y-axis are the IDs of the concurrently started containers. And we can see of the 6 most time-consuming stages, 4 of them are related to the configuration of Passthrough I/O. And the detailed statistics show that over 70% of the time cost comes from the configuration. By further analyzing the breakdown, we identified that there are 3 key configuration steps of the Passthrough I/O that leads to the high overhead. The first is a memory mapping configuration for DMA. As we have mentioned, to directly move the data between the network interface card and the guest memory, it involves translating the address visible to the device, which is called IOVA, to the host physical address. And to configure the mapping from IOV to HPA requires us to determine the physical page allocation for the micro virtual machine. And as we're in a multi-tenant cloud environment, those pages needs to be cleaned of the dirty data to ensure that the data from the previous user are not leaked to the next user. And we found that this configuration process can cause high time overhead, and particularly the page clearing or page zeroing operation. And the second configuration step is the initialization of the virtual function. And the startup, the micro virtual machine will open the virtual function through the VFIO driver on the host. It will retrieve necessary device information and performs corresponding setup. The VFIO driver manages the different virtual functions as a device set and with global states. The global states summarizes the status of all the virtual functions. And the global states, they are used when the host try to perform operations like bus reset. And the global states are affected by the operations on the virtual functions. The VFIO driver uses a global mutex lock to control the operations, making the operations on the global states and the virtual functions mutually exclusive. But this lock also serializes the operations on the different virtual functions, which causes problem when we try to operate on the different virtual functions concurrently. And the third configuration step is the guest network driver initialization inside the micro virtual machine. So when a VF is set up and it is passed to the micro virtual machine as a PCIe device, the driver inside the micro virtual machine will probe and configure the device to generate a Linux network interface for the container to use. Our measurements show that this process can also take seconds. Targeting these bottlenecks that we identified, we present our design. And our design addresses them using three key innovations. The first, our design FastIOV reduces the memory mapping overhead by using a lazy zeroing mechanism, because we identified that it is the zeroing operation of the physical pages that contributes the most to the overhead. The key idea is that we want to decouple the memory clearing operation from a physical page allocation, and we only want to zero a page when it is actually accessed by the micro virtual machine. And this requires us to monitor the memory access operation initiated by the micro virtual machine. And showing this figure, when the micro virtual machine initiates a data read or write to a guest physical address, this guest physical address needs to be translated to host physical address using a hardware module called the extended page table. And this process bypasses the software. So how do we monitor and intercept this process? And the solution, our design uses a EPT fault-based memory access interception and perform the lazy zeroing. An EPT fault generates the entry in the extended page table that maps the GPA to HPA the first time when a page is accessed. So, and showing the figure here, when the micro virtual machine accesses a physical page for the first time, the extended page table will trigger an EPT miss and queries the KVM software module to generate the mapping. And this process allows us to intercept and perform the zeroing operation. And second, FastIOV design proposes a hierarchical lock framework to parallelize the initialization operations on the different virtual functions. So this framework uses the Linux mutex and read-write lock combinedly to control the operations on the parent load and the child load. Here, the parent load corresponds to the global states of the device set of the virtual functions, and the each child load corresponding to a virtual function. The framework maintains a global read-write lock. The access on the global states requires the write permission of the read-write lock. And the access to the virtual functions first requires the read permission of the read-write lock, followed by acquiring the permission on the mutex lock. The separation of the read-write permission controls their operation on the parent and the child node, makes them mutually exclusive, while the operations on the different child can be parallelized, and the read permission can be held by different processes simultaneously. And the mutex we use for each virtual function is intended to control the operations on the same virtual function and ensure the data correctness. And finally, our design uses a asynchronous driver initialization mechanism to overlap the time that the guest network driver takes to generate the Linux network interface inside the micro virtual machine. We overlap this initialization process with the subsequent startup stages, and particularly the startup of the container application inside the micro virtual machine. This overlap is possible because the Linux network interface generated is not used until the container application actually starts running, and it is independent of the subsequent startup stages. With the three designs, we evaluated our design on a testbed running the open source Kata secure container with a server configuration resembling the production environment of Alibaba Cloud. And we compare with baseline, including the original SRV-based container network and the existing optimization methods relevant to the bottlenecks that we have identified, like the memory pre-clearing methods. And we also include a series of FastIOV variants for obligation study. For the evaluation, we concurrently start 200 containers on a physical machine, according to the statistics from Alibaba Cloud. Our evaluation results show that our design can significantly reduce the overall start time of the container. Specifically, we can cut the time cost related to the virtual function by over 90% and reduce the overall start time by 65%. And our obligation study shows that each component of our design contributes meaningfully to the overall acceleration. And we also evaluate our design under different level of workload. For example, we vary the per container memory allocation, and we vary the startup concurrency. And the results show that across the different settings, our design can still achieve the time reduction that is above 40%. Besides the container startup time, we also evaluated our design, the benefits of our design on the performance of the common container applications like the image processing application or DNA inferencing application. The results show that their completion time can be reduced by a range of 12% to 53%. To summarize, our work focused on accelerating the concurrent startup of SRV-enabled secure containers, and we identify three key configuration steps of pass-through I/O that causes the high startup overhead, and we present three designs to address them, including a DMA memory lazy zeroing mechanism and a hierarchical lock framework and a synchronous driver initialization scheduling method. And that is all my presentation, and we have released our code on GitHub. Thank you, and I'm happy to take any questions.